Hey everyone, welcome back to the channel. I asked you guys in my intro video what would be something you guys would want me to do a video on. And one thing that I saw was someone asked about relativity and gravitational lensing. So that's a little hard to keep to a high school level, so this might be a little bit higher than high school, but I'll try to keep the math to a minimum because the math for relativity is graduate school level. So I have a link that I'll put that has derivations for general relativity, but I'm not going to go through that because that would be like an entire lecture. So this will also have pretty pictures in it, and if you are just here to see pretty pictures, then I'll put a timestamp for you guys. But if you want to learn about relativity, then stay here and we'll get to it. So in high school physics, we do Newtonian mechanics, which is considered a static frame or not a moving frame. We learn how light has no mass, so it's not affected by gravity, but objects with a mass are. So in this frame, we have an object falling down with the force due to gravity from gravity's acceleration g, and light just travels straight across. It's not affected by it. This isn't the case for general relativity, though. In Einsteinian, rather than being in a static frame, we're in an accelerating reference frame. So how does this change things? If the accelerating frame is the same magnitude as the gravity field, so if we're accelerating upwards at 9.81 meters per second squared, then the object falling will be the exact same as it would on Earth. Say we're in a spaceship and we're going upwards with a certain acceleration, an object will fall straight down just like it would on Earth. However, a beam of light will act differently in the two frames. So, like I said before, in the static frame, light will just pass through with no deviation from its path. But in the accelerating field, it will appear to drop just like the object does. This apparent drop is the effect of gravitational lensing from the bending of space-time. One thing to note is that when light passes around objects with large masses, light will be deflected in multiple directions. That's why we can see either a ring or multiple images of the same object, and I'll show examples of both of those later. Just as more mass causes more acceleration due to gravity, more mass causes greater lensing effects. So this equation here is really the only equation I'll show, but I'll leave a link in the description to an article that has all of the derivations for this. If you understand tensor calculus, you'll be able to understand this. If you don't know tensor calculus, just follow along with this equation. Just like in Newtonian mechanics, the more mass you have, the greater the effect of the acceleration you'll have, and the closer you are to the object, the more of an effect you'll have. So we have in the equation here, g being the gravitational constant, m is equal to what I wrote down as mass of the foreground object, meaning that what is going to be bending the light. C is the standard representation of the speed of light. And then B is the impact parameter. What this is essentially where the light is passing in relation to the center of the mass of the object. So for this example here, if light is passing right at the surface of the sun, B is equal to 6.957 times 10 to the 8th meters. That's the radius of the sun. So the mass of the sun is 1.989 times 10 to the 30 kilograms, and B with the circle with the dot is the radius of the sun, 6.957 times 10 to the 8th meters, and then we have the standard values for the speed of light in a vacuum and the gravitational constant. When you do all of this out, you get 8.492 times 10 to the negative 6 radians. When you do the equation out, that's the units you get in the end, and I converted it to degrees and arc seconds for you guys to see. So 0.000487 degrees or 1.75 arc seconds. So a very small amount of light will get deflected by the sun, but it's a measurable amount. In 1919, general relativity was put to the test with a solar eclipse. So if you have a decent telescope, you'll be able to see stars near the sun during a solar eclipse. And according to relativity, they will not appear to be in their true position. Like I had on the last slide, if there was a star where the light passed right at the surface of the sun, we should see a deviation of 1.75 arc seconds. And every star around the sun will be measurable. The 1919 eclipse, the experiment conducted is known as the Eddington experiment. The leaders of the experiment were Sir Arthur Eddington and Frank Watson Dyson. Along with their collaborators, they experimentally measured the positions of stars near the sun during the eclipse. They were broken into two teams, and one was in Principe, West Africa, and the other in Sobral, Brazil. And they did have some troubles with the experiment. The team in Principe was clouded out, but still got photos of the solar prominence, but they weren't good enough to actually see the stars in the images, so their data was essentially scrubbed. And the team in Sobral was using two telescopes, and funny enough, it was the backup telescope that got the clearest images. So this is probably the greatest example in science of why you should have backup equipment. Because of the poor image quality, the images from the main telescope in Sobral and the images from Principe were discounted due to being either clouded out or the focus not being right. And interestingly, with the out-of-focus images from the main telescope in Sobral, they actually had detected what would be calculated for Newtonian mechanics. I highlighted out-of-focus images because when you have something with a lot of noise, or it is out of focus in this case with an image, you're not going to want to use that for data because it's not going to look right. So this is the statement from Eddington on why they discounted the other telescopes. So the greatest weight must be attached to those obtained by the 4-inch lens at Sobral. From the superiority of the images and the larger scale of the photographs, it was recognized that these results would prove to be the most trustworthy. You might think, is that a little fishy to be discounting data, especially some that would be more in line with Newtonian than Einsteinian? But the beauty of science is that experiments are repeatable. And over here on the side, I have a list of historical events where people did this measurement as well. They got around 1.75 arc seconds, which is what was calculated for Einsteinian mechanics. And this is evidence that general relativity works. It's correct. Today, you can actually do this experiment as well, but the process to actually do this and do data analysis is very complicated. So what you need is calibration images from the night before or the night after the eclipse. So the purpose of this is to calibrate for turbulence and reduce the centroid noise. This is done because the atmosphere will actually cause effects with the images because the atmosphere moves around, so you could get images that are blurry just from the atmosphere itself, and that's why space telescopes are always preferred to use. So the difference between today and the past experiments is that we can do digital photographs now, where the team in 1919 was using photographic plates. You want to have your photograph be as close to the solar limb as possible and have an area across of about 5 to 10 degrees. And you'll need to determine what this magnification is with your setup. So every telescope is going to have a different focal length, and you're also going to have different cameras. So you need to figure out what is best for your setup. And during the eclipse, you're going to have to take multiple short exposure images. And I'm going to have a paper linked that describes how it was done for the 2024 eclipse. And I'm also going to link that for the data analysis because that uses software and is very complicated. As of recording this, they have not published their results yet, but give them time. I mean, this was just a few months ago. So gravitational lensing is observable in other ways as well. Space telescopes view it all the time. You can actually use large telescopes on the ground to view it. Or there's the Event Horizon Telescope project, which actually saw black holes. So the two images on the left are of the black hole in the galaxy M87 and Sagittarius A star. So Sagittarius A star is actually the black hole at the center of our galaxy. I also used an image from Interstellar because Kip Thorne, who is now a Nobel Prize winner, was a producer of this movie, and he did calculations for when they were going around the black hole, and you can actually see how close it is to reality. So to explain what you're looking at, the ring that's going around the top of it is actually from gravitational lensing. So the disk that goes around the black hole, just like you could think of the rings of Saturn, that light is being bent up and around and down below it. So you're actually seeing the backside of the black hole at the same time as you're seeing the front. Now, for when galaxies are lensed, it's a little different because it's a galaxy being lensed by another galaxy. So this diagram here shows it pretty well, where the light is bent just like we saw with the black holes, but it's also bent by all of the stars as well. And with the stars, you might be thinking that there's very little deflection, but when you think about how there's billions of stars in galaxies, that adds up over time. So now for some examples. So this is known as a cosmic horseshoe, and this one is almost a perfect ring or a perfect lens around. So that ring is actually a galaxy behind the galaxy that's the orange dot in the center. This right here is a galaxy cluster, and it actually has multiple examples of lensing. Now, they aren't perfect rings just because the lensing isn't perfectly aligned, but it is still possible to see it. And this one's really cool just because it has so many examples in just one frame. And now we get to the fun images of it, this one being known as the molten ring. To me, this one just looks like a smiley face, and I bet that's what you guys are thinking as well. And this is my favorite one, and why I put a picture of a cat on the thumbnail. This is known as the Cheshire Cat galaxies. As you can see, you do have a face, and if you put this up next to an image of the Cheshire Cat, it actually does look pretty similar. And now we get to when we have multiple images of the same object. So this is a very famous one known as Einstein's cross, where those four dots around the center one are actually all the same thing. So how do we know that it's the same object? Well, when you do the spectroscopy of it, you get the exact same thing for all of them. So the flux of them is going to be different, but as you can see, the peaks of the wavelengths are the exact same for all of them. I also wanted to include the source for this image just because this shows you that you can see gravitational lensing from the ground-based telescopes, but you do need large ones. So like this is from a 4.2 meter telescope. And then here are some other examples of multiple images that were lensed. I'm not going to read off the official names of all of them just because that's a lot of letters and numbers. There is a naming scheme to it though, just trust me on that. But all of these images that are around the central one, they're all the exact same thing, which is really cool to think about. Alright guys, so that's it for this video. If you have any questions, then leave a comment for me. Or if you have any suggestions for future videos, then do let me know. And make sure to like the video and subscribe. See you guys next time.